Okay, good morning. Sorry to keep you waiting. Let's start. So the quiz 7 is already available at the counter of H113. And the late submission and resubmission will be accepted at the final on Friday, March 2nd. We are going to start the final at 9:20, I believe. Okay, the first period of the final week. So the solution is in the Moodle. And the scanned short paper is already posted, but it's not completely, grading is not completed yet. But I'm thinking of, I'm trying to return it at least by the final at the latest. And the special office hour, this time, anyhow, I can stay at my room at the late afternoon of February 28th, but I just want to set it in this way, okay? The special office hour, I'm available at my office during the first and the second and the third final exam period. That means between second and third exam period, we have a short lunch break, and at that time, I'm also going to have lunch. So that time I'm not available there. Okay, and if you have more students who cannot fit into my office, then we will move to a seminar room around very near to my office, and then we will give explanation or discussion on the problems of to prepare for the final. Okay, so. But you don't have to come to my special office hour. And if you are not available this period, then you can just send me an email and make an appointment. Okay? But honestly speaking, I'm going to have an interview for the community service learning because I'm serving director of the service learning now. So I don't know whether I have enough time to just fit my schedule to your request. And today, we're going to study this in the side screen, review for the final exam 2017 and 18. So that is the one I distributed on Wednesday. But if you haven't received it, then I have it on that desk. Okay? But the other two finals, those are the old finals of 2015 and 2014. 2016, I got a research leave, so there is no exam that year, all right? And then the comment sheet and the tests, okay? I hope I can announce something at the end about the test, but this test, I think, may change pretty soon from next year or the 2 years later. But this design, I think we made it in the year 2003. And at the time, I was the director of the faculty development office. And then this is the one I designed. So I have I really spent lots of time creating this test, bilingual test. And so this is very important, even if I receive lots of, comments through the comment sheet. But this is separate, right? And this is anonymous. And also, I will read it and use it for my improvement of my course for the next year. Although that next year will be my last year in my career. And also, this is for the improvement of the educational system at ICU. And not all, but some of them are read by the officers. Okay, so please write your comments, and that will be helpful to us, to our university, and also for the students who are going to take this course or receive education at ICU. So please, take time to write it. Okay, so, but as I announced, we're going to review the final exam review for the final exam. Okay. So review for final exam 2017-18. So we are going to review some of the topics we have studied in this term. I think we have studied a lot. Okay. So I don't know, you may have already forgotten everything, but we started out from this truth table. Okay. So truth table, we also studied three logical operations, four logical operations: negation, and the let me call it logical and, logical or, and implication. And in each of those expressions, we have the truth value. Okay, but if you look at logical and, logical or, and implication, then you will find easily that there is only one place different from the other truth values. Okay, for example, for logical and, you have t at tt position. That means both of the left-hand side and right-hand value, truth value, p and q in this case, are true. Then you get t, but otherwise f, right? And then for or, logical or, if both of them are false, then you get false. And the implication is false only when the left-hand side, that is the if part, p is true, but q is false. Only in that case we assign truth value f to this logical formula. Okay, so you can just look at this table and then copy the condition, think about the condition and determine the value, but that takes a lot of time. Okay, so the best way is to think about such, say, typical assignment of the truth value. Okay, so for example, this one, the following is valid for the statement PQR. This is part one is a truth or a true or false global. Okay, so we want to determine whether this is true, this statement is true or not. That means we want to decide whether these two logical expressions, okay, that is this one, okay, these two logical expressions are combined by these three lines. That means logically equivalent. That means all truth values for any combination of truth values of PQR, these truth values are equal. Okay? If that's the case, we can combine them, right, by this congruence. That is called the logical equivalence. So we need to check the logical, say, truth table, okay, and then check whether the truth value agrees with each other. But in the case, the left-hand side, if you check carefully, okay, I will explain a little bit. If you check carefully, then this is the only place you get f. Okay. On the right-hand side, these three are the only positions you get f. But if you say, for example, this TFF case, the left-hand side, a formula gets truth value t, and the right-hand side formula, you get truth value f. That means there is some position or a combination of the truth values of PQR, you get different truth values. So we say that these two things, the leftmost part and the central part, okay, these are not logically equivalent. So this doesn't hold. So we say that this is false. Okay. So here I just wrote only the place the truth value is f. Okay. And if you can find these things, then that is fine. Okay. Because the rest of them are just t. Okay. So we just can find those things. But if you look at the top part, top line, we want to compare the truth value of the first one and the second one. Okay? But if you know a so-called distributive law, then the middle part is logically equivalent to the rightmost formula, because you have R and combined with this logical OR, right? R logical OR, R logical OR. And then you have the logical AND sign in middle. Okay, so if you carefully look at the formula so-called distributive law, okay, then you can combine these things to express it as, say, negation of P and negation of Q and or R. But the negation of P and negation of Q is logically equivalent to negation of P or Q by the so-called De Morgan's rule. So if you can find that the middle part is logically equivalent to the rightmost part, and if you compare the leftmost part and the rightmost part, then this part, these two parts are completely different, right? So you can find easily some combinations of truth values of PQR that these formulas do not agree. Okay? So that is also possible, but this is a little bit advanced. Okay? So in this course, the best I suggest you to do is to complete the truth table. Okay? So truth table is the basic part, but a very useful tool to determine the truth value of the logical expressions. Okay, so for example, you have this, right? Then we want to complete the logical expression, truth value of, logical value of these things, okay? But since the last one we have here is OR, right? So OR, as I told you that there is only one F, okay? There are many T's because the OR means either first one or right hand side one say true, then you get true. So there are more possibilities of getting value true, T. So it's better to think about the case when R is F, and then this part is equal to F, okay? If these two things are F, yeah, then you get F, okay? But R is F, that is easy to check, okay? So that is this or this or this or that, okay? And how about that? This is F, that this expression is false. That is only when the inside function, this part is true, right? So this is equal to true. Then it's also easy to determine. P and Q is true. That is when both P and Q are true. That is this part, right? So these are, you get TT. P and Q, so you get TT. So if you get F negation, so you get F and F. Okay, so both of them, so this is false only when both of them are F, but F is here. Okay, you have to write down all these things. Okay, so the only case you have F is this, right? So this is the only place you have F. Okay? But if you look at this formula, then this part you can expand it by using the De Morgan's rule. So you can also write it as not P or not Q or R. Okay? Because both of them are logical OR. You don't have to use a parenthesis. Okay? Then, as you may know, that this is false only when everything is false. That means P is T true, Q is true, and R is F, right? So this is the only place you get F for the left-hand side formula. So if you find this one, then the right-hand side, just check whether there F appears some other place. Okay, so the right-hand side is a little bit more complicated. Okay, but if you check one by one, then I hope you can reach the conclusion that these two formulas do not agree. Okay? I want to take more time, but since we need to cover many problems, so I want to move forward. Okay? All right. So the next one is as a matter of fact, this true or false problem is say a little bit difficult. Okay, because the true or false problem is not just a calculation, but unless you understand the say theory behind, you cannot say true or false. Okay, so it's a little bit difficult. But since as I told you many times that to getting some techniques, okay, that is somewhat fun, okay, but it's also very easy to forget unless you use it, okay. So the learning experience I want you to do through this course is that I want you to experience that you can understanding mathematics if you take time and try to understand it completely. Okay? So experience of understanding mathematics is the important part of this course. Okay? So that's why I added some of the true or false problem like this. Okay? So the next one is let A be an n by n matrix if a matrix equation Ax is equal to 0 has infinitely many solutions. Okay? So please recall that system of linear equations or matrix equation Ax equal to 0, that is, say, compatible, corresponding. So if you have a system of linear equations, then there are three types of solutions. One of them is there is no solution, that is zero solution, or exactly one solution, or infinitely many solutions. Okay? And we have a corresponding condition that the equation has no solution, exactly one solution, or infinitely many solutions. Okay? This says that the Ax is equal to 0 has infinitely many solutions. Okay? And the A is a square matrix. Okay, in this case, it says that n by n matrix is a square matrix. So Ax equals 0 has infinitely many solutions if and only if this is reduced row echelon form. Okay, reduced row echelon form of A is not I. Okay, and if you go back it, then this is written as the invertible matrix theorem. Okay, but for example, just start with a simple example. Okay, if A is 1, 0, 0, 0. Okay, then if this is a coefficient matrix, okay, if this is a coefficient matrix, then the right-hand side is 0. So, for example, this one is the augmented matrix. Okay, okay. So even if you don't understand this much, please think about this part. Okay, if this were an augmented matrix, okay, then in this case there are infinitely many solutions. Okay, I said that for the system of linear equation there are three types: no solutions, exactly one solution, or infinitely many solutions. Okay, because if you consider the system of linear equations corresponding to this, okay, there is no symbol for unknowns, but just assume that this is x1 and x2. Okay, two symbols, x1 and x2. Then this equation says x1 times 1, x1 is equal to 0. Okay? But for x2, there is no condition, right? x1 is equal to 0, that means x2 can be anything. x2 can be anything, that means there are infinitely many solutions. Okay? So the system of linear equations corresponding to this augmented matrix, there are infinitely many solutions. Okay? So Ax is equal to 0 has infinitely many solutions. But you can also think of this type of thing. Okay? But this A part, that is coefficient matrix part, is exactly the same. Okay? But if you have this augmented matrix, then the second equation says that 0 equals 1, right? So this is inconsistent. So that means there is no solution. So even if A is just exactly the same, but depending on the values of x equals to b part, okay? I always say that b, okay? The right-hand side is 0, 0, then this has infinitely many solutions. But if you have 1, 0, 1, then you have no solution. So this one is false. Okay, what about A, B, and m by n matrix and m is less than n? Then a matrix equation x equals to 0 has infinitely many solutions. Okay, let me. That is 1, 3. Okay, then this one, x, A is a m by n matrix and the m is less than n. Okay, so it's a little bit difficult. So let me just assume that this is 2 and this is 3. Okay, then A is a 2 by 3 matrix. 2 by 3 matrix means you have 2 rows and 3 columns like this. Okay, and it said that the AX is equal to 0. That means right hand side is equal to 0. Okay, so the augmented matrix you have is something, 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 and then the right hand side is 0, 0. Okay, this is the augmented matrix. And you want to know whether AX equal to 0 has infinitely many solutions. Okay, so the infinitely many solutions. So if this is consistent or not, okay, if there is a, we can determine whether this has a solution or not. That is a consistent or inconsistent. Consistent means that there is at least one solution. Inconsistent means there is no solution. But in this case, if you set xa, in this case x1, x2, x3, x3, okay, x is equal to x1, x2, x3. Since right hand side is 0, okay, if x1, x2, x3 are all 0, then that is always a solution. So this is always a solution. For example, if you put 0 into x, then you have a solution, right? X is equal to 0 is a solution. So this is always consistent. Okay? So then we have to determine whether this has infinitely many solutions or not. And infinitely many solutions or not, that is decided by the number of parameters. Do you remember? Number of parameters. Okay? And that we just choose number of parameters, okay, at the place where we do not have the leading ones. Okay? So in this case, you may have leading one here or here, one here and there, or only this place or not. Okay, we cannot tell. But the leading ones, there are at most 2 leading ones because there are 2 rows. Okay? Okay, so that means at least one of the columns, okay, do not correspond to the leading ones. That means we need to have parameters to express solutions. So that is, we have infinitely many solutions. Okay, I just chose the case 2 by 3, but that is the case for general case of any size m and n. Okay, let's come back. All right, this is another problem we discussed at in section 6. Okay, derivatives. F of x is a function such that f prime of c is equal to 0 and f double prime of c is equal to 0. Okay, then f of x is either increasing, decreasing, or a constant at x is equal to c, and f of c is not it cannot be a local extremum. Okay, so important fact is the following 2 statements. If you have a function and that is positive, if the derivative is positive at certain point, that is x is equal to a, then the original function, okay, g prime is the derivative of g, then the g is increasing. Okay? So if that is negative, if the derivative is negative, then that is decreasing. That is all we can have. Okay? So otherwise we cannot tell. But by this statements, we can determine whether g of x is increasing, decreasing, local maximum, local minimum. Okay? If you take derivatives consecutively, okay, and discuss those things. And in this case, I just say that this f can be increasing or decreasing or local maximum or local minimum. We cannot decide. So that's why that is false. Okay? But let me just give you some idea why we can say that. Okay? Idea behind this, we have a function x to the n. Okay? It says x to the n, x to the n. And you should know this type of thing. Y is equal to x, x squared, x cubed, x fourth, x5, and x6. Okay? And then just tell that this is increasing or decreasing a local minimum or local maximum at x is equal to 0. Okay? Then we want to know the graph of these things. Okay? Y is equal to x. This function is something like this. Okay? Probably you know. Okay? Then what about y is equal to x squared? Y is equal to x squared is, I think I better use different color, but I'm a color blind and I also I confuse myself, so I don't know whether this is good or not. Okay, so this is y is equal to x squared. Okay, then what about the other ones? Okay, x cubed. X cubed, say, goes, let me just use one more color. Okay, I don't know which one you like it, but let me use black. Okay, then it goes like this. Okay, so this black one is x cubed. So basically, if x to the 2n plus 1 or x to the odd power, you have this type of thing. Okay, and if it's even power, because if it's even power, okay, if it's even power, it's always on the positive side, right? It cannot be the negative side, right? But if you have an odd power, then if you put big, large, say the -3, -5, and so on, then that is negative value, right? So if it's negative power, I mean the odd power, then it goes down to -infinity. Okay? So this is the kind of typical function we have. But in this case, we know that at this point is a local minimum. Okay? And in this part, this is not a good picture, but it goes like this and then goes like this. Okay? So this is increasing. Okay? But for example, if you have x cubed, you take a derivative, you get 3x squared, and then this is derivative, and then the second derivative you get 6x. Okay, so even if you plug 0 into x, say derivative gets 0, and second derivative also gets 0, right? But if you plug, say, values in the third derivative, that is 6, so you get positive. right? Third derivative, you get positive. And in that case, you can tell that that is increasing. But so in the similar way, you have, if you have x fourth, then f prime is equal to 4x cubed. So this is 0, okay, at x is equal to 0. Okay. Then what about the second derivative? You get 12x squared. Again, if you plug 0 into x, you get 0. Okay. What about the third derivative? You get, say, 24x. Again, you get 0, right? And then what about the fourth derivative? Then you get 24, and this is positive. Okay, so this is the kind of typical one, and from this, you can get many examples that if you plug 0 into the derivatives, you get 0, but still that can be local minimum or local maximum, or increasing or decreasing. Okay? So the typical one you should think about is x to the nth power. Okay? But if you come back to this problem, okay, then it said that f is a function such that f prime of c is equal to 0, f double prime of c is equal to 0. Okay? Then, for example, x to the fourth. Okay? If you take a derivative, you get 4 times x cubed. If you take second derivative, you get 12x squared. So if you plug x is equal to 0, you get 0 here, you get 0 here. Okay? So the derivative and the second derivative, you get 0. But as I gave a picture here, x fourth is something like this. So at x is equal to 0, this is local minimum. Okay? So you cannot say that even if x is equal to 0, say at c is equal at c, f prime, the derivative is 0 and double prime is 0, then you cannot tell that that is increasing or decreasing. And also if you take the cube or x cubed or so, then that is also that derivative is 0 and second derivative is 0 at x is equal to 0, but it is increasing. Okay. All right. Next one, 1.5. Oops, 1.5 is not there, so let me just oops. I'm afraid I made a mistake, but let me, okay. All right. So you have f of x is an antiderivative of f of x. Okay. So capital F of x is an antiderivative of f of x. That means if you take a derivative of capital F of x, you will get small f of x, right? And you want to take a derivative of capital F of e of x, e to the x, because you want to show whether this is antiderivative of a product of some functions. Okay? So if you take a derivative of this function and then you get this, then that's an antiderivative. This is an antiderivative of this function, but otherwise we say that they are not. It's not. Okay? So this is the problem of the chain rule. Okay? For the derivatives, chain rule is the sort of most difficult ones. Okay? So you should review chain rules by taking time. So if you have g of x is equal to f of h of x, then the derivative of g of x is if f prime, that is the derivative of capital F, is equal to small f, then by chain rule, derivative is equal to the derivative of the outside function and then keep the inside, and then multiplied by the derivative of the inside function, in this case h prime of x, right? So this formula is important, and you have to express some functions in this way. Okay? Then by the chain rule you have this, but we know that f prime of x is equal to small f of x, so this f prime part can be replaced by small f of h of x, so you have this. Okay? But in this case, we know that this h of x part, since we want to calculate the derivative of this function, so that is e to the x, so h of x is equal to e to the x. Okay? Then the derivative of h of x, that is easy, that is e to the x, right? So you can replace this h prime of x part by e to the x, and also h of x part by e to the x. So derivative of g of x, that is g prime of g prime of x, you should get f of e to the x and times e to the x, and that is a 1 you have here. Okay? So what this means is, okay, in the problem it said that the capital F of x is an antiderivative of small f of x. Okay? If we know that, and the inside function in this case is e to the x, then we can calculate the derivative of f of e to the x, okay, by the chain rule. If you take a derivative of this function, then outside function, if you take a derivative, then you get f of x. Now, so just replace e to the x part, x part by e to the x. Okay? Then you have to multiply by the derivative of the inside function, in this case e to the x. So you get f of e to the x times e to the x. That's a 1 you should get. Okay? Important fact is that the antiderivative and derivative are kind of, say, reverse operation. Okay? If you take a derivative and you get some function, in this case small f of x from capital F of x, then antiderivative of small f of x is capital F of x. Okay? But that type of relation can be used to calculate derivatives for the composite functions like this. Okay? And the answer each of the following. You write the truth table of this one. I'm afraid I erased this one, so let me just look at the solution. Okay? But for this particular solution, please be careful. This is not a complete solution of the truth values. Okay? Truth table. So write a truth table of this. Okay? P implies Q, or negation of R and Q. Okay? So we use the truth table. Okay? Truth table for the implication and logical or and logical and. Okay? Besides negation. So P implies Q. Okay? If you look at the truth table, then P implies Q is false only when the left-hand side, in this case, P is true, there are 4 places. But the right-hand side, Q, is false. So TF combination, you get F. TF combination, if you look at P and Q, through TF combination, then there are only 2 places, okay? T and F. So you got F. Okay? Then now we want to determine the truth value of the whole thing. Okay? And I write only I wrote F at only 2 places. Okay? But you have to be careful. There are some other places we get F. Okay? There are some other places we get F. But what I'm doing is, since we want to find the logical OR of these 2 expressions, okay? In order to determine the logical OR, we want to find the combination of the left-hand side truth value and the right-hand side truth value both of them are F, because the only FF case you get F, right? So we first calculated the left-hand side, and we found that the only 2 places we got F. Okay? So we don't have to calculate these remaining parts. Okay? And if you can find that truth value of these 2 places, then we can determine the truth value of the whole thing, because this is combined by logical OR. That means we want to know the place, the combination of truth value, you get F and F. Okay? And we already located the combination of truth values where the left-hand side gets FF, right? So what remains to know is that the right-hand side, we just check only these 2 places. Okay? Then these 2 places, TFT, so we are looking at Q and not R, right? So Q is TF, right? But this is AND. AND means both of them is true. Then you get true. But in this case, not R, this one is not R means T, so FT, right? And the Q is FF. So anyhow, Q part is always F. Q part is always F. That means this logical AND, you get always F, right? But be careful, I'm repeatedly saying that the other parts, I'm not claiming the other truth values are F. Okay? So we first found these 2 places, truth values at F, and the right hand side, just check the truth value of the corresponding part. Because of this truth value F of Q, you get FF. So altogether, you have TT, FF, TT, TT. Okay? All right. Next one, 2, 2. This is very important, so I think I should better explain it, but I'm afraid I erased it. Let me just copy that one, because that's very important. Okay, so this one, find the 3 by 3 matrix satisfying the following. Okay, so T is a 3 by 3 matrix, and we want to get right hand side if you multiply T from the left. Okay, that's a little bit difficult. It's an advanced problem, but we know the way to solve it. Okay, in this way, we have that if you apply some elementary law operation. We have done elementary law operations quite a lot, right? A, B, C. And we know the way to change A, B, C to this one, okay? If you apply elementary operations twice, okay? For example, by the first step, if you apply 2, 1, semicolon, minus 3, okay? Then that is add to the second row, okay? Minus 3 times the first row, right? So minus 3 times the first row is minus 3. Oops. Minus 3, okay? So this one you get add to the second row, this is 1. The minus 3 times the first row, so that is minus 3a. So just add minus 3a to the second row, so you get minus 3a plus b, right? Then what about the next one? 3, 1, semicolon 1. That is add 1 times the first row to the third row. 1 times the first row, that is a, right? So if you add it to the third row, that is c, you get A plus. Okay? Then you get this one. Right? That means you obtained the right hand side by consecutively applying two elementary operations. Okay? But the elementary operations correspond to the elementary matrix, right? So in order to get this, if you just obtain by, say, applying this elementary operation, then you have a matrix 2, 1, minus 3, 1, 1, 1, like this. And if you multiply this matrix, this is so-called, this is the one called E2, 1, minus 3. Okay, if you multiply this matrix from the left to this ABC, you get this one. Because the 1, 0, 0, you get A, minus 3, 1, 0, you get minus 3A plus B, and then 0, 0, 1, you get C. So if you multiply this matrix, then you will get this. Okay? Why do I get this? That is, starting from the identity matrix, if you apply this operation, 2, 1, minus 3, 2, 1, minus 3 means add to the second row, minus 3 times the first row. Minus 3 times the first row, you get minus 3 here, so you get this matrix. Okay? So if you multiply this matrix from left, you get this. And then next one, if you multiply 3, 1, 1, that is the matrix of this type. Okay? If you multiply this matrix, then you get this. That means first multiply this one, that is this one. And then next, this one from the left. So the order should be this way. Okay? So if you multiply these two matrices, you should be able to get this matrix, and that is the solution. Okay? But in this case, there are a better way. And so you have, if you have these two things, the left-hand side matrix is to do the same thing as you apply the elementary operation called 3, 1, semicolon 1. So starting from this matrix, and then apply this operation, then 3, 1, 1, that means the third row. Okay, third row is obtained by as the sum of the third row and 1 times the first row. So just add the first row, you get this one, from this you get 1, 0, 1, and you will receive the matrix down below. Okay? So that you can have the solution. Okay. All right. Okay, this is the matrix multiplication of two matrices, and I don't know whether I have it or not. Okay, we didn't take time to multiply these two matrices very much, but in order to say, for example, if you want to find the 2, 1, this is the second row and first column entry, then in order to find that one, first take the second row, because this is the second row, and then the first column of the second matrix. Then 2 times 0 and 1 times 2 and minus 1 times minus 2, and then add them together. Since that the first one is 0, second one is 2, third one is 2, so you get 2. Okay? So in that way, you can calculate the multiplication, okay, of matrices. Important fact is that for the matrix multiplication, AB may not be equal to BA. Okay? So even in this case, you have two different matrices as a result of multiplication. Okay. All right. Then determine whether or not the matrix A is in the previous problem is invertible. Okay. In order to check whether the matrix is invertible or not, okay, we just find the reduced row echelon form of the matrix. Okay. In this case, this one is 4. Okay, so we start from this matrix. A was equal to 1. 1 0 minus 2 2 1 minus 1 minus 2 2 0. Okay, so starting from this, you get a reduced row echelon form. Firstly, I think this one is applied, say 2 1 negative 2, and then the 3 1 2. Okay, if you apply these two things, then you should get 1 0 minus 2, because the say 2 times the first row is subtracted from the second row, so you get 0 1, and then 2 times the first row is minus 4. If you subtract it, you get added, then you get 3, and similarly you get 0 2 minus 4, then you have this. Okay, please recall that if you want to find the inverse of this matrix, okay, if you wish, we start from A and I, okay, and use a reduced row echelon form. I'll find the reduced row echelon form, and if you have I and then matrix B, then if you reach this one, then A is invertible, right? Invertible. That means even if you look at the left-hand side, okay, that is stated in the theorem. If you look at the left-hand side, that means the reduced row echelon form of A is equal to I. Then the matrix is invertible. So the only thing is you don't have to add this I to find whether A is invertible or not, and just find the reduced row echelon form of A. In this case, if you change it, then you will get this type of form, and if you apply elementary operations twice more, then you get I. So you can tell that the I is the A is invertible. Okay, how can we get that from the last one to I? It's just easy, right? So if you multiply minus 3 times the third row, add it to the second row, you get eliminate this 3 without changing other entries. And then if you add 2 times the third row to the first row, you eliminate this negative 2, so you get identity. Okay, so please review section 3. Right? I'm afraid we are running out of time. So I'm afraid that I'm spending most of the time for the section 2 and 3. Okay? Find the reduced row echelon form of the matrix below and find the solution to x1, x2, x3, x4, x5. Right? So you have this one, and then reduced row echelon form, or reduced row echelon form. You have to first have the 1, so like this, okay, the leading 1. So if you look at from the left, the first non-zero entry is equal to 1. Okay, here you have 2, so you have to make it to 1. Okay, you cannot change this only this part by replaced by 1. You just multiply 1/2 to the all entries of the second row. you get 1, 0, 2, minus 1, and 0. Okay? So you have this part. And then add using minus 1 times that row to the first row, you get eliminate this one and then this one. Because the reduced row echelon form, if you look at from the left, then the leading one, that is a non-zero leftmost part, is 1. And that is the only non-zero entry in that column. Column means the vertical one. Okay, so you have 0 and 0 here, and 0 and 0 here. Okay, so then I think that is the one you get this one. Then from this you can read out the solutions. But say if you are not familiar with this type of thing, the best way is to write down the corresponding system of linear equations, assigning the first variable to x1, x2, x3, x4, x5, x6, and then the last column for b part, right hand side part. Then this is, for example, the first one is x1 plus 2x2 minus 5x5 and 1x6 is equal to minus 2. Okay? And then this one is x3 plus 2x5 minus x6 is equal to 0, and so on. Okay? Then just pick parameters from the column which is not corresponding to the leading ones. In this case, leading ones are here, here, and here. Leading ones is the leftmost entry in the reduced echelon form. Okay, so 1, 2, 3. These are the reduced leading ones. So choose parameters, okay, corresponding to the column which doesn't have a leading ones. So second column, fifth column, and sixth columns are those ones. Okay, the right hand side is just on the right hand side of the equation. So then this is, in this case, S, and this is T and U, and if you write it in this way, then x1 and so on can be read without difficulty. Okay, so don't skip each step. If you have this, then write down the system of linear equations corresponding to this augmented matrix. Okay? All right. We also studied Lagrangian interpolation. Do you remember Lagrangian interpolation? Okay. So the solution is just given below. But the important fact is that in this case, 1, 2, 3, 4, 4 values of x are given. Okay? And we want to have assigned value at each value of x. Okay? In this case, at 1, you should get 1, 2, you should get minus 2, 3, you should get 4, and 12, you should get, 4, at 4, you should get 12. And in order to do it, this is the typical formula we have by the Lagrangian interpolation. Important part is the numerator part. Say, for example, if you want to find a value at 1, then the second one, third one, and third one, we call it second term, third term, and fourth term. Okay? You have x minus 1 factor. So if you plug 1 in, this doesn't appear. If you plug 1 in, this becomes 0. If you plug 1 in, you get 0. So the value at x is equal to 1 can be calculated only from the first one. Okay? If you plug 1 in, numerator becomes 1 minus 2, 1 minus 3, 1 minus 4. But if you look at the denominator, that is exactly the one you are substituting 1 into x. So you get 1. So at 1, you get 1. Okay? And if you plug 2 in, then the first and third and fourth term disappear because you have x minus 2 factor in each of these terms. Then look at the second term. if you plug 2 in, 2 minus 1, 2 minus 3, 2 minus 4, you get the same value with the denominator. So this part becomes 1. So the coefficient sitting there is minus 2. So the value at x is equal to 2, you should get minus 2. That is the one you have for x is equal to 2. Okay? So the construction we have studied, okay? And in this way you can write down the polynomial having these properties. Okay? But you can also have much more polynomials of the similar type with the same properties. Okay? So this is the same values. Okay? But the f of x is the one in the previous problem. Then f of x and the a can be any polynomial. You should get the same value. Okay? Because if you plug 1 in, this part disappears. 2n, this part disappears. 3n, you get this part disappears. 4, we have the same thing. So a can be anything. Okay? A can be any polynomial. But this particular problem asks to obtain a polynomial g of x of degree 4. Okay? In order to get the degree 4 formula, f of x is of degree 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. There are 3 x's. So altogether you get x cubed at most. So this part is of degree at most 3. Okay, so then if you add degree 4 polynomial, then you will get degree 4 polynomial. So if a is a non-zero constant, then the right hand side, this fact, the last term is of degree 4. So altogether the degree is 4, and you have a polynomial of desired condition. Okay. All right. So find the limit problem. In this case, we have done similar problems. Okay. And the first look at the denominator part. Then from this you can get that the n goes to infinity. Okay. So if you have such a term, we have to be careful. Okay. In this case, we divide by the highest power of n. Okay. In this case, n cubed. So we want to divide by the highest power of n, that is n cubed. Okay, n to the 3. But if you just say divide by n cubed only at the denominator, then that may change the value. So we have to do the same thing for the numerator as well. That's why I multiplied 1 over n cubed to the numerator and the denominator. Okay? If you simplify it, then you get these factors, numerator and the denominator. And as n gets larger and larger, this part becomes 0, this part becomes 0. So the only remaining part is 3 over 1, that is 3. Okay? What about this? Okay, in this case, you do not have n. Instead, we have x goes to 2. Okay? X goes to 2. Again, since it's a fraction, we have to be careful on the denominator. Okay? What do you have for the denominator? If x approaches 2, x cubed approaches to 8, right? 2 times 2 times 2 is 8, right? That means denominator becomes 0. Okay? Denominator becomes 0. But the one good thing about it is if the polynomial gets 0, then there is a factor x minus 2. Okay? So you can divide x cubed minus 8 by x minus 2. So you can factor it in this way. And then numerator, you can do the same thing. And the x minus 2 term can be cancelled out. And then you have this one. And if as x goes to 2, the denominator goes to, say, 12. Okay, the numerator is 0, so non-zero Let's say 0 over non-zero, so that is 0, and you can get it. Okay? And you may find difficulty factoring a polynomial. That happens, okay? In this case, x cubed minus 8. But in that case, we have a very nice technique, right? That was synthetic division, right? So x cubed minus 8, if you want to divide by x minus 2, then you can use the synthetic division, okay? So you want to write down x cubed minus 8, since x goes to 2, this goes to 0, right? Or say if f of x is equal to x cubed minus 8, then f of 2 is equal to 0, right? In that case, we can express f of x, in this case x cubed minus 8, as say something q of x times x minus 2 plus 0. Okay, this is the remainder. So you can find q of x. That means you can factor this polynomial as a product of x minus 2 and a polynomial. Okay, then you can use the synthetic division. Okay, so you write 1, 0, 0, minus 8, because this corresponds to x cubed, this corresponds to x squared, this corresponds to x, and this corresponds to x to the 0. Then we write 2 here, and then 1 comes down, multiplied by 2, add them together, multiply by 2, add them together, multiply by 2, you get 8 and 0. And so this is the remainder. And this is the polynomial for q. This is x squared, x, and then constant. So you have that the q of x is equal to x squared plus 2x plus 4. Okay, these are from here. Okay, so in that way you can find q of x. Okay, so you can factor the denominator and then cancel x minus 2 out, and you get this. But in this case, since you know that the denominator goes to 0 and numerator also goes to 0 as x approaches 2, you can use the L'Hopital's rule as well. Okay, L'Hopital's rule, do you remember? Okay, L'Hopital's rule, in this case, we want to find out x goes to 2 and x squared minus 4x plus 4, and then x cubed minus 8. Okay, so both of them goes to 0. Then this is equal to derivative of the numerator, in this case 2x minus 4, and the derivative of the denominator, you get 3x squared. Okay, so as x goes to 2, then this becomes 2, 4, so 12, and then 2, 4, 0, so this becomes 0. Okay, so you can get it. But I'm afraid I'm running out of time. So if you, we can discuss the remaining part on Monday, or on Monday we also can discuss the old final exams. Okay, so let's do the one more review on Monday, and we will have final a week from today. Okay. Okay, so some of you might have come late. So this is a special office hour. That the first and the second and the third final exam period, that is about 9:20 to 16:20 on Thursday, March 1st. Okay? Or otherwise, please make an appointment by email. Okay? So I didn't take time to write tests, but a test is teaching effectiveness survey is very important, and at ICU, we do not call it just a student evaluation of teaching, but we call it as teaching effectiveness survey, and that includes 3 parts: course evaluation, learning evaluation, and teaching evaluation. Okay, so I want you to evaluate the course as a whole. Okay. Anyone who can tell me to bring this one to the first floor? Okay. Then please put the SC in front. And submit it. Okay. So on Monday we will continue the review of the review sheet and also the final exam.